Hi everyone. So a quick introduction. So I'm Ligeng, currently a rising fourth-year PhD student at MIT, working with Professor Song Han. And today I'm going to present on behalf of Wei-Chen Wang, because his flight delays. And the topic we are going to present today is on-device training under 256 KB of the memory. So let's get started. So deep learning has achieved great accomplishment in recent years, and there are a lot of applications powered and enabled by the deep learning. But we want to squeeze in deep learning into tiny IoT devices, because there are billions of IoT devices around this world based on the microcontrollers, which is far larger than the numbers of mobile devices. And also microcontroller devices, they are low cost and everyone can afford it. And also it's a low power, so it encourages green AI and also reduce carbon dioxide exposure. And also it will enable vast of various of applications such as smart home, smart manufacturing, personalized healthcare, as well as precise agriculture. In our previous work, MCUNet, we have enabled tiny deep learning inference on the IoT devices. We are addressing the memory bottleneck issues by designing tiny engine infra, as well as co-design and co-search the neural architecture to push out the memory usage. And we have enabled a practical ImageNet level accuracy models on the tiny microcontrollers. And in this work, we are going to push the research frontier to one step further. We want to perform not only inference, but also the training on the tiny IoT devices. If we can, by enabling the training, the AI systems need to continually adapt to the data collected from the world, thus it can continuously learn from the dynamic environments. On-device learning has several advantages. It provides the users with a customized experience without hurting the privacy. And also because it does not need to transfer the data to the cloud. Thus, it also allows models to customize their models with a low cost. And also it enables the device to continue to learn, thus enables the lifelong learning. But this task is not trivial because the training is much more expensive than the inference. And it is very hard to fit it into the edge hardware because of the limited memory budget. As shown in the figure, we can see that the edge devices, even for microcontroller and the Raspberry Pi, the memory budget is very tight. Like the microcontroller only have hundreds of kilobytes of the memory, and the Raspberry Pi only have hundreds of megabytes of memory. But when we want to perform the training, even for a tiny batch size equals 1, a single forward and backward could take around more than 400 megabytes of the memory, thus exceeding the memory limit. And we need to find a method to overcome the issue. As you can see in this figure, for current popular frameworks like TensorFlow, PyTorch, and also some edge frameworks that enables training, requires a lot of the memory. And even for the cheapest framework like the MNN, it still requires 40 megabytes of the memory and has greatly exceeded the memory limit of tiny devices. Therefore, we propose 4-stack solutions to address the memory bottleneck, and which we will explain in detail. Okay. So to enable the tiny training on the edge devices, we have proposed 3 techniques circulating from the software to the hardware, and enable the training becomes possible on the tiny microcontrollers. The first technique we are going to introduce is the sparse layer and the sparse tensor update. So in conventional 4 update, as you can see in this figure, so blocks annotated with blue means that it requires actual memory for the training purposes. And you can see updating the whole models can be very expensive because it requires us to save all intermediate activations and need to store all updated weights in the S1. Therefore, the required memory can be expensive, but usually it delivers the best accuracy. So what we propose is called method called sparse update. Basically, we are finding important layers and important weights and only update these layers and weights during the training process. So main intuition here is that in our ablation study, we found that some layers are more important than others. And by only updating these important layers, we do not need to backpropagate to early layers and only need to store a subset of this activation. Therefore, by using the sparse update instead of the full update, we can greatly reduce the training memory. And it also provides us some interesting insights and observations. So we find that the first is that we fine-tune the layers, and we found that the important layer distributions are actually different. So we find that for the ConvNet models, the later layers are usually more important than the early layers, which means that we should focus on the later layers to improve the performance rather than the later layers. And also in the popular mobile net architecture, the first pointwise convolution in each building block contributes more to the accuracy. But the things are different when we go into the language models. We notice that for the language models, actually it is the middle layers that contributes most to the accuracy. And the attention and the first FFN layers contributes more, whereas the second FFN actually does not play an important role. And with these observations, we can focus on these important layers and only update this during our training. And we find that, so with our search sparse update scheme, so the sparse update can achieve higher transfer learning accuracies using 4.5 to 7.5 smaller actual memory. As shown in the figure, we evaluate our sparse update on 3 models, and we compare the sparse update with different memory budget and compare with the fine-tuned 4 baseline. We find that the sparse update not only reduces the memory footprint, but also improves the accuracy to a certain level. Therefore, it's safe to use the sparse update, and it does not degrade the accuracy. And the second technique we are going to introduce is called quantization-aware scaling. So because of the limited memory budget, it's not feasible to run the full precision or floating number trainings on the edge devices. Therefore, we need to quantize the models and using a quantized data flow. However, while the quantized data flows is much more efficient in both of the memory and the computation, they are very hard to optimize. So we noticed that if you directly optimize the quantized models, it will lead to a significant performance drop. For here, we benchmark the MCU net or benchmark the mobile net compared with the floating versions and also the quantized versions. You can see if we use the quantized versions, it leads to around 10% top line accuracy drop because of the quantized graph has the mixed precisions, which lead to the different gradient scale. And also it lacks the batch norm stabilization layers, such as the batch normalization, which makes the trainings unstable and converge to a suboptimal point. Therefore, we need to address this problem. We plot the gradient scales and notice that. So the main optimization degradation comes from the inconsistent gradient scales. As shown in this figure, where the IP32 is plotted with blue and the int8 is plotted with green, and we compare the gradient scales between the weight and the gradients. And we notice that so the scale of weight and gradients does not match in the quantized graph. Therefore, it leads to makes the optimization much harder. And we need to compensate this behavior to make the scalings consistent between the original graph and also the quantized graph. So what we get is that we propose a automatic adaptive compensation term for different layers. And for each layers, after we calculate its corresponding gradients, we compensate it with a scaling factor. And this scaling factor is derived by the quantization scale. And this scales compensates gradient scalings and makes the gradient and the weight in a same level. So for the optimizers can easily optimize this graph. And as you can see here, after we apply this scheme, we compensate the quantized graph. So quantization and wheel scaling aligns the weight to the gradient ratios with the original floating graph, thus we can improve the accuracy. You can see here, we compose when we directly using the quantized graph, it leads to a significant performance drop. And even we use some adaptive optimizers such as Lars and Adam. So for the Lars, it completely fails on the quantized graph, and the performance is even worse. For adaptive popular optimizers like Adam, though it can almost match the performance of the floating baseline. However, it requires 3 times of the memory, and thus it's not feasible for the tiny devices. And our proposed course, where it's still using the SGD, it does not reintroduce actual memory and can improve the accuracy compared to the floating baseline. And we also plot the training loss and the validation loss below, as you can see here. So using the quantization of wheel scaling would improve the training loss and the validation loss both, and it makes the optimization easier and better. So after we propose 2 algorithm level innovations and reduce the training memory and also the optimization difficulties, we next need to propose and system integrations to translate the theoretical numbers into real measured speed ups. So why we need to build a new training infra, because existing frameworks cannot fit into the microcontrollers. So it usually has a heavy runtime because it has a lot of dependencies, and also they perform most of the tasks like the autodiff at the runtime, resulting in the heavy runtime and also the low edge dependency. And also because of the design is mainly for the developer efficiency and flexibility. So memory cost is heavy, and they have a lot of intermediate and unused buffers allocated. And also it has to compute the full gradients, does not support the sparse update. So far, we propose our new design, which we call it tiny training engine. So the core ideas of the tiny training engine is that it is a compilation first framework, and it offloads the most workload from the runtime to the compile time. So for example, in the conventional framework, when a graph is fed into the models, it performs the autodiff and other operations at the runtime, and the training graph is unoptimized. But in our training engines, the full graph is directly differentiated in the compile time, and we aggressively optimize the training graph to achieve the best edge efficiency. Therefore, in our tiny training engine, the runtime is minimized and also the cost is reduced. Here's the comparisons between the tiny training engines and also the conventional framework like TensorFlow Lite. So we can achieve with up to 20 times memory footprint reducement. And also we can achieve up to 23 times faster speed compared to the previous baselines. And also it was noting that if you are using the TensorFlow Lite macro, it will lead to out of the memory and cannot run the training of the most popular mobile framework like MobileNet V2 and MCUNet. And also we can scale the tiny trainings to different devices, like the Qualcomm CPU, the Jetson Nano GPU, and also the Raspberry Pis. And here we show the benchmark results on the mobile net V2 with an input resolution 128 and 128. Our engines can support various platforms, and our sparse update shows that consistent speed up from 1.4 times to 3 times. Okay, and I think there's here's a demo for our work. How many time do I have left? We can show it.
About 5 minutes.
Yeah, so it should be enough.
As the classifier to predict person or no person, which is a binary classification problem from VWW dataset. We first visualize the model's prediction on a small test set. As you can see, the results are quite random. The accuracy of the prediction is very low because the model is not trained. Now the testing is done. We perform training with some data to improve the performance. The labels are provided through the serial port for each sample, and the training is done on the microcontroller within the small memory budget. As the training goes on, we can find that the accuracy is generally getting better. The training is finished. After the training, we test the model again on the original test set. Now we can get 100% accuracy, showing the effectiveness of the training.
Yeah, so basically you can see previously, so microcontrollers cannot recognize the object in front of the camera accurately. But with the on-device training and just a few labeled examples, it can now properly.
Finally, we show that the trained model can be applied to real life. Here we point the camera to a person, and he is successfully detected. Thanks for watching.
Yeah, and here is a real-world demo. And our work has been reported by the MIT News, and also there is some media coverage. And our work from the inference to the training has been open sourced publicly on the GitHub. You're welcome to try and play with it, and we welcome open collaborations. Okay, that's all my presentation today. Thank you. If you have any questions or comments, please let me know.
Okay, we have a comment or a question,
Yeah.
maybe.
Hey, thanks for the very nice. So I think one of the situation you'll face when applying this kind of algorithm to on-device training is your data set will be very long tail. For example, if you have a device that monitors the heart rate to detect a heart failure, then the heart failure will happen like very infrequently, and most of the time the heart rate is just normal. So is there a way you guys can deal with this kind of long tail training data set?
Oh, that's a very good question. So yeah, so here for this work, so basically we are solving the system side issue. Like we are proposing as algorithm system co-design to enable on-device training. But you are right, if we want to the on-device training to be practical in real world, we need to address the data set distributions and also a lot of other problems. So actually we developed, so in this work, we didn't consider the long tail distribution problem. Yeah, we are mainly focused on the system side, but our lab mate has working on some transfer learning algorithms, try to address the long tail problem. Basically, they are proposing some new on-device training algorithm to address the forgetting issue and also the long tail distributions, which should come out later this year. But so far, we can only process the standard data set, like some normal distribution. Yeah, we can handle specifically for long tail scenarios.
Okay, maybe one more question if there's any. Okay, let's thank our speaker once again.
Thank you.
So bear with us. We have one more talk, and we're going back to multi-messenger astronomy. So poor Janina had a delayed flight, so she wasn't able to present earlier. And so she's going to give her talk now. So, and then we'll go to the dinner.
Okay. I hope you can hear me. Okay, great. Yeah, hello. So yeah, I'm trying to not to keep you too long from the food. So let's get started. I'm giving a short overview about the work of Kate Scholberg's group at Duke University. So in our group, there is Joshua Queen, which is a graduate student. And then we have a postdoc, Vanta Biglian. And we are very happy to also welcome a new postdoc in the near future, which is Lucy Avco. And then there's myself, I'm a postdoc. And yeah, the work can roughly be covered by low latency pointing to a supernova with neutrinos. So first of all, why bother at all with neutrinos? I mean, they are pretty hard to detect. So that's why I have this nice graphic here. And what you can see here basically is neutrinos are arriving very quickly after the burst. And they have a high luminosity. So more than 99% of the energy is emitted in the form of neutrinos, which if you can detect them, they are quite ideal to figure out when a supernova has happened and also where the supernova is in the sky, because the neutrinos are so weakly interacting that they basically point directly back to the source. So it's interesting to construct an early warning system from neutrinos. And also, of course, any detection has not only an enormous physics potential for astronomy, but also for particle physics. So there's still a lot that we don't know about neutrinos, and supernova explosions could help to get some information at least. So there is already an existing early warning system, which is called SNOOS. So there's the 1.0 version, which consists of a simple coincidence between the participating experiments. And they are already providing alerts since 2005, actually. And then there's an upgrade, I think it's still ongoing, which improved latency, which now also includes neutrino-based pointing and triangulation between the different experiments. So this is an overview. There are already quite, so not all of them are running yet, but there is quite some contributions with a lot of different detection materials. So there are water-based detectors, scintillators, LED, noble liquid dark matter detectors, and then there's liquid argon. And for the rest of my talk, I will focus on DUNE, which is a liquid argon-based experiment, and that is what we are studying in more detail. Okay. So DUNE is a time projection chamber experiment. It's planned to have consist of 4 modules, which 10 kilotons each, and it will be located in South Dakota in the underground. So the underground is helpful to suppress cosmic ray background, and the large argon volume means there will be quite some statistics. This time projection chamber, there's this illustration to show how this works. So when the particles come in, they produce ionization and scintillation light. And this is read out with the wires that you can see here. So the ionization, for example, they create signals on the wires. And this is time dependent when the charges actually arrive at the wires. So from this, you can derive a 3D image, which is ideal for tasks like supernova pointing, because you can actually get a 3D track reconstruction and point back to the source. Dune is mostly detecting electron neutrinos, which is also great because the other large supernova neutrino detection experiments are actually detecting anti-neutrinos. So there is an interesting complementarity there. And electron neutrinos are especially interesting because at the beginning of the burst, most of the emitted neutrinos are likely likely electron neutrinos from, at least from the models that we know up to now. Yeah, I'm thinking I'm switching to that. Okay. So how to detect neutrinos with Dune now? There are 2 dominant channels. One is the charge current interactions. Here the neutrino interacts with the argon nuclei, and an electron is created in an excited potassium atom. And the other potential interaction channel that's interesting for us is the elastic electron scattering, where the neutrino scatters with an electron. And we get out again, of course, the neutrino that we cannot see, but also the scattered electron. The first interaction is about 10 times more likely. So the cross-section is about 10 times higher. However, it turns out, if you look at the angular distribution of the outcoming electron, this is actually flat. So that's the red curve that you can see here. So we cannot really gain directional information from this, at least not if we look at the overall distribution. However, for the elastic scattering, it's possible. So that's the blue curve. So statistically seen, the electron direction is related to the initial neutrino direction. So this is, at least for now, the interactions that we want to see to point back to the source. So it's really important to be able to distinguish between those 2 types of interactions, and also potentially all others that occur that are less likely. For the energy spectrum, I just want to briefly mention that these neutrinos are actually quite low energetic. So this also makes it harder to actually detect these neutrinos and also to reconstruct the direction. And so we already studied this in detail in an offline reconstruction. So this results that I'm showing you on this slide are not suitable when to immediately get an answer when the experiment is running. But this is if you have enough time. And it turns out this is actually overall working nicely. So what we did, we simulated the supernova events, but also noise and background. And then we reconstructed the single events, which consists of identifying them, determining the energy, determining the direction. Here, it's especially important that you also need to know the head-tail direction. And this is not coming. So you need to do something else to get this information, which was an algorithm that we call daughter flipping, which I will explain in more detail later. And if you have all of these events, you can combine them. That's currently a maximum likelihood estimation, and you can get out a direction. And so this consisting 40 kilotons of so for 40 kilotons of liquid argon, we get a resolution of 3.7 degrees. And if you reduce this to only one module, it's 7.4 degrees, which is already not too bad. However, this does not take into account that one might misidentify some of this elastic scattering events. And here, currently only an assumption exists. So in this table, I'm assuming that about 4% of the charge current events are classified as electron scattering events, which clearly reduces the pointing resolution because they don't carry any information on the direction. And the figure up there, you can study this in much more detail. What happens? It turns out it's a little bit more important to correctly identify the elastic scattering events than the misidentification, which is on this axis. But nevertheless, we need to have some kind of channel tagging once that there's data to correctly to find as much of the electron scattering events and have as little misidentification as possible. This algorithm to run this takes quite a while, definitely longer than a minute. In a minute, is this what we are aiming for the online pointing in the end? And also currently this algorithm does not take into account events below 10 mega electron volts. So we are not using all of the information at the moment because we cannot nicely extract the information that we want from the low energetic events. And all of these are enough reasons to continue. And we want to continue using machine learning. So the strategy is to start slow, to first of all, just convert the existing offline algorithm to an online version, and then add more and more optimization, more and more machine learning. We call this Kaizen approach, which, so if you have been in Boston, is a term that Kate introduced, and it basically means something like a static improvement over time in a methodical way. So that's what we want to do. So this is an illustration. So actually the only number that really holds is this one here. So this is what you can achieve with the offline full reconstruction, as you have shown on the last slide. And we are hoping that it's possible for the online reconstruction to get this result much faster and to get some reasonable value already after 1 minute, which can then be sent to systems like SNOOS to alert other experiments, to alert telescopes, to look into the right direction. So that's what we are aiming at. And to do this, I have some kind of outline and some ideas. And I want to start at the beginning, so that's why I have this slide here, which is actually not work that is carried out at Duke. However, it's in Georgia, Karakioshi's group at Columbia. And what she's doing, she's looking at the data that is directly created by the TPC. So it's like a video stream with certain, so 11.5 megapixel frames. And she's trying to figure out where you find a supernova interaction within the background. So all of this is radiological background and noise. And only here we have the supernova interaction. And you can see this is difficult. It's very, it happens on a very small, also a very small scale, this interaction. And she's, so I have this slide because she's using machine learning to do this. And yeah, in case you are interested in this kind of, so there's this nice publication that gives an overview how this could work. So now assume we found some, so the supernova happened and we found this kind of events. So what to do to get the pointing resolution? So we have the trigger primitives. The next step is the deconvolution, the hit finding. Up to now, so the top is the current situation. We have this Gaussian hit finder. This is followed by an event reconstruction, which consists of extracting the actually primary tracks from the supernova events, the energy, the direction, the head-tail disambiguation, and finally the maximum likelihood approach to combine everything and get the direction of the burst. And on the lower part of the slide, I have the efforts and ideas regarding machine learning. This list is for sure not complete, and yeah, but that is some of this I will be talking about this in more detail now. So first of all, concerning the hit finding, there's some effort to improve this towards lower energies. And then for the event classification, I think I already made a point that it's important to correctly identify electron scattering events. So there are some machine learning efforts there. And also regarding the head-tail disambiguation, we want to improve this with machine learning. And finally, combining the events to a burst. Also here, it might be helpful to limit ourselves to those events that are really important for a good pointing resolution and drop the rest as early as possible. And we hope that here machine learning can help us as well to understand which feature of the events are actually important for the pointing. So the first item that I want to highlight is the channel tagging, so the distinguishing between these two kinds of events. And so imagine Dune has already been built, taking data, and this is a sky map that we get out of there. And these are all supernova events. However, yeah, it's, I mean, it's just a lot of events, but we need to distinguish between them. And if we are able to, so the blue one is the elastic scattering ones. You can see we get an idea where the supernova was. So around this direction. And so in the end, it's an event classification problem. We have the events, we want to separate them in those two categories. At Duke, there has been already some effort, which was done by Erin Conley to use a boosted decision tree. And this already showed some promising results. So she got about 5% misidentification of the charge current events as elastic scattering events. However, this algorithm is still quite slow for our purposes. Then there are other ideas like a CNN for object detection and also 2D CNNs. However, none of this actually yet reached the performance of this decision tree. So there's still a lot of work going on in this direction. And moreover, thinking what else needs to be done. Most of these events on the previous slide are red, as you can see here. And it would be, I mean, it's tempting to think if there is not a possibility to use them also to find the direction of the supernova. And indeed, you can find subcategories between this de-excitation of the potassium-40 atom actually into Fermi transitions and Gamow-Teller transitions. And if you are able to distinguish with them, they also carry directional information. So this is some line of research that we are following at Duke, and hopefully this might be possible at some point. And then we can strongly increase the statistic of events that can be used for the pointing. So that's about the channel tagging. Another item that needs to be studied is if we have a reconstructed track, did it go into this direction or did it go into that direction? Because the TBC events do not tell us this. So there's this daughter flipping algorithm, which I will just describe very, very briefly. So what is happening here is to study the angles between the daughter particles, the blue ones, and the primary track. And it turns out, because the daughter particles are created in the forward direction, that the mean of the cosine angle is larger than the mean of the cosine angles if you assume the wrong direction. So that's the idea behind the daughter flipping. How well this performs, you can see in the figure on the right. So blue is without daughter flipping, red is with daughter flipping. However, these results are currently only based on simulations. So Joshua Queen is now planning to study this with real data with the iceberg experiment. The iceberg experiment is a small 1 ton liquid argon TPC with dune electronics. So it's already somewhat close to what we will get in the end. Then we, of course, also need events. For the events, you can use Michel electrons that are created from cosmic ray muons. And he will examine how well the daughter flipping works if we have this real kind of backgrounds and noises. And this will also give a nice data set for machine learning. And we will see if the performance of the daughter flipping can be improved. And if you want to know more about this, here's a poster. So the last item that I want to talk about in detail is this low energy events. Why do we care about the low energy events? So there are supernova events at low energies that would be nice to be detected, but also for this daughter flipping algorithm, we need daughter particles, and those might be low energetic. So it would be nice to be actually able to detect them. And here we have a cooperation with Michael Wang and other people from Fermilab. So they published their work here on 1D CNN to extract low energy signals from more liquid argon TBC waveforms. And the next step here is an autoencoder. And Vanta Big was working on this in the last year to see how this detection efficiency can be improved, and to use also this autoencoder for waveform denoising. And he also has a poster. If you want to know more about this, then you can talk to him. So to sum it up, I hope I could show you that it's worth it to detect supernova neutrinos to get an early warning of that a supernova occurred and where in the sky it can be found. So we have the supernova early warning system, which is called SNOOS. And Dune will be one of the experiments which is highly capable to detect these neutrinos, which large liquid argon volume and an excellent 3D imaging reconstruction. And studying what the Poynting resolution offline, we get about 2.7 degrees for 40 kilotons and 5 degrees for 10 kilotons, and 5 degrees if we start to assume a misidentification of charge current events as elastic scattering events. And for our next steps, we are planning to improve these results with machine learning, and especially transfer this to a fast online version, which what we will be doing is, or what we are currently actually already doing, is transfer this code to a standalone version that then can be enhanced with machine learning. And there are a lot of ideas around that I've shown you regarding channel tagging, directional reconstruction, but also low energy events and the combination of the events to the burst. So thank you for your attention.
Any questions? One question before we eat, anybody?
What is the expected rate of detection of neutrinos from supernovae when Dune is running?
What do you mean with rate? Like,
well, we know that there's one supernova every second in the universe, and the big radio telescopes, SK, DSA 2000, are expected to get some chunk of those. What number of the core collapse do you actually expect to get with Dune?
I cannot give you an exact number. I think for the distance, you can see something up to 100 kiloparsecs. I mean, at some point, of course, it's not possible to do pointing, but just to detect events.
You mean 100 megaparsecs? Because 100 kiloparsecs means it's in our galaxy.
Oh, sorry.
Yeah.
Yes. Yeah.
Yeah. Okay.
Yeah. Yeah, I can look the
Yeah, so
figure up
it's
for you.
it's pretty much the same as LIGO with Kilinovi at the moment then.
Yeah, that could be true. Yes.
Any other questions? Okay, let's thank Janina